Hello everyone. In this AV, we would be taking up the chapter called Thermodynamics. To start with the chapter, first we will understand few basic terms involved with the study of thermodynamics. First of all, we would define thermodynamics, and it is defined as the branch of physics which deals with the conversion of heat into other forms of energy. So, in this branch of physics, we deal with the processes involving heat, which is denoted as Q, work, which is denoted as W, and internal energy, which is denoted as capital U. So the conversion of heat into mechanical work and vice versa is studied in the thermodynamic portion. So how do we define it? The branch of physics which deals with the interconversion between heat energy and other forms of energy is known as thermodynamics. Now we have to understand two terms. One is the thermodynamic system and the other one is surrounding. So as per the definition, a specified portion of matter on which the effects of thermodynamic variables such as temperature, volume, and pressure are to be studied is known as a system. It will be more clear when we take up an example. And surrounding is anything other than or outside the system which tends to influence the property of a system or which exchanges or tends to exchange energy with the system is called its surrounding. Let's take one example. Suppose we have some particles of gas enclosed in a cylinder which is fitted with a piston. So here we have a cylinder which encloses the gas particles or gas molecules, and it is fitted with a piston, and we want to study about this gas. So this cylinder becomes our system, and anything outside this cylinder, the immediate surrounding, is known as the surrounding of the system. It can contain air particles, it can contain other particles, but we are more interested in the system. Now we can have two types of system. One is in which we allow the exchange of heat energy in between system and surrounding, and the other one is when we do not allow the exchange of heat between the system and surrounding. So that will come along as we progress with the chapter. Now, first of all, before we go into the laws, we will understand something called thermal equilibrium. Now, if we have, let's say, two bodies, body A and we have body B, and we assume that they are in contact with each other. So once they are in contact with each other, there will be definitely transfer of heat energy take place between the two. Now that will depend, the direction of heat flow will depend on which body is at the higher temperature. If we say that body A is at higher temperature, then heat flow will take place from body A to body B. Or if we say that body B is at a higher temperature, then heat flow will be from body B to body A. Now the question arises is for how long? So there will come a time when they both will have or they both will reach a state where their temperature becomes the same. Now at that point the heat flow will stop, and that point will be known as thermal equilibrium. So thermal equilibrium is a state where both these bodies have the same temperature, or is a state where no heat flow will take place between these two bodies. So this is all about thermal equilibrium. So as you can see, the temperature of a body is the measure of its hotness or coldness. Now, this is another thing, that is temperature, which decides the direction of heat flow, and the heat flows only till the system or the state of the body reaches something called thermal equilibrium. Once the thermal equilibrium has reached, there will be no more transfer of heat energy from one body to another body. Now we go to the Zeroth Law of thermodynamics. This is very strange, as in any of the physics topics the laws start from first law, second law, but this is the only topic where we have the Zeroth Law. Zeroth Law of thermodynamics gives us the concept of temperature. Now, why do we call it Zeroth Law and why not the first law or second law? Because we have the first law and the second law of thermodynamics, which were discovered or formulated long before we discovered the Zeroth Law, or the law which tells us about the temperature or the concept of temperature. So we have been using this term in our first law and second law, but we had not defined it. So when the scientists discovered this law, instead of calling it the third law, though it was very basic law which was supposed to be placed before the first and second law, so as 0 comes before first or second, 1 or 2, so this law was called as Zeroth Law of thermodynamics. Now what does this law say? This law says that, let's assume that we have two bodies, body A and body B. Now body A is also in thermal equilibrium with body C, and body B is also in thermal equilibrium with body C. That means temperature of body A is equal to temperature of body C, and temperature of body B is also equal to temperature of body C. What we mean is, suppose TA is the temperature of body A is equal to temperature of body C, and also we have another body B and the temperature of body B is equal to temperature of body C, then Zeroth Law of thermodynamics states that temperature of body A will be equal to temperature of body B, which means body A and body B will also be in thermal equilibrium with each other. How do we state this law? It simply states that if two bodies A and B are separately in thermal equilibrium with a third body C, this is what we said, A and B both are in thermal equilibrium with body C, then A and B are in thermal equilibrium with each other. So this is the Zeroth Law of thermodynamics, which talks about the entity called temperature. So we define temperature based on the Zeroth Law as temperature is that property of a body which will tell us whether the body is in thermal equilibrium with one another or not. We also state this line as temperature is the property of a body which will decide the direction of heat flow. Now, as we know that work and heat are interrelated, so we will talk about how we relate work and heat. If we want to raise or increase the temperature of a body, then we have two ways of increasing the temperature. Firstly, by supplying heat to it. If I want to increase the temperature of an iron nail, I can simply heat it, or I can also beat it with a hammer. In both the cases, the temperature of the iron nail will be increased. Another example we can take is, if I want to warm my hand, then I can simply take it near where the fire is burning, or where there is fire, or I can also rub my hands and heat energy will be produced. Now, in both these examples, we see that both heat and work, they cause or they make the temperature rise or change the state of the body. Now, so we say that work is a form of heat energy, and how they are related. 1 kilocalorie of heat is equal to 4.18 into 10 raised to the power 3 joules. This is the relation between heat and work done. By the way, 1 kilocalorie is the amount of heat which will be required to raise the temperature of 1 kg of water by 1 degree Celsius. So, this is the relation between kilocalorie and joules, that is heat and work done. 1 kilocalorie is equal to 4.18 into 10 raised to the power minus 3 joules. Or we write it as W is equal to JQ, where the value of J is 4.18 into 10 raised to the power 3 joules. Now, we have seen that energy can be transferred from one body to the other body either by the means of temperature difference or by doing some physical work. Now, if we transfer heat from one body to another and that transfer takes place due to the difference in temperature, then the energy transferred will be called as heat. Whereas if the energy transfer takes place between two bodies but it is not because of the difference of temperature of the two bodies, then the energy transferred between them will be known as the work done. And whenever there is a difference between the system and surroundings temperature, then the heat will be transferred. Now, it will be transferred from the system to the surrounding only when the system has got higher temperature, or it will be transferred from the surrounding to the system when the system is at a lower temperature or the surrounding is at a higher temperature. But when there is no temperature difference between the system and surrounding, then the transfer of heat will not take place. Now, depending upon the direction of heat transfer, we have the sign convention. Now, if heat is given from the system, then the sign is taken negative, or when the heat is taken from the surrounding or gained by the system, then the heat is taken with the positive sign. So, we will quickly sum it up as this sign convention used for the study of thermodynamic processes. Heat gained by the system will be taken as positive. Heat lost by the system is negative. Work done by a system is positive. Work done on the system is negative. Increase in the internal energy of the system is positive, and decrease in the internal energy of the system will be taken as negative. Now, we try to understand what is work in detail, and then we will understand about the internal energy. So, focus on this diagram. Here we have a system where a gas is inside a cylinder which is fitted with a movable piston, and we have placed certain weights on the piston. Now, this is the position of the piston, and these weights are exerting a force on the piston, so it is not allowing the gas to expand. If we assume that P is the pressure of the gas and A is the area of cross section of this piston, then force will be calculated, or force can be calculated as force is equal to pressure multiplied by area. Now what we do is we remove the weights from here. That means the gas is allowed to expand. Gas is doing some work. Now if the gas expands, the piston would be pushed a little upward, and we assume that ds is the increase. Now the displacement, the small displacement ds, is because we have removed the weights and this gas is allowed to expand, or the gas has done some work. So work done is given as force into displacement, but here there is a small displacement, that is ds, so the work done will also be small, so that work done will be denoted as dw. So we have the equation dw, or the small amount of work done, is equal to force multiplied by displacement. Now force is nothing but pressure multiplied by area, so instead of force we write this pressure multiplied by area into displacement is small displacement, that is ds. Now area into this length, the small length ds, will be the small increase in volume. So the equation takes the form dw is equal to pressure multiplied by volume, or small volume. Small amount of work done is equal to pressure multiplied by small change in volume. dw equal to p multiplied by dv. Now if the gas volume increases from V1 to V2, then we can calculate the entire work done by the system by integrating this equation and taking the limits to be from V1 to V2. So we integrate this equation. Integration of dw is equal to integration from the limits V1 to V2 p dv. So here the pressure of the gas has not changed, it remains a constant. So the integration steps would be, this is our initial equation, and as we have said that the pressure of the gas does not change, so the term P, that is pressure, here will be treated as constant. So integration of dw is w is equal to, pressure is a constant, so it will come out of integration sign, and we have P outside the integration sign, integration from V1 to V2 of dv. Now integration of dv will be v, so the equation changes to P integration from integration of dv is v from the limits V1 to V2. Now integration says we substitute the values and we have upper limit minus the lower limit. So the equation takes the form work done W is equal to P as it is, and instead of this we substitute the upper limit, that is V2. So the work done in expansion of a gas from volume V2 to V1 is given as W equal to P V2 minus V1. So this is the equation. W is the work done is equal to pressure multiplied by change in volume, that is V2 minus V1. Now depending upon the situations we plot different graphs. If the pressure of the gas remains constant, then this is the graph, and the work done is given by the area enclosed by this. And if the pressure changes, or pressure is a variable, then we have this graph, and the area covered under this graph gives the work done. To take out the total work done, we divide it into small portions and we take this small portion as dV, and then we follow the same integration process. So we can obtain directly the work done by the gas or a system by the area enclosed between the PV curve and the volume axis. So this is the area under the PV curve or the volume axis. Now we have to keep in mind that if work done is by the system, that it is to be taken as positive, and if the work is done on the system, then as per the sign convention we have to take it as negative. And the work done of a system or by the system not only depends upon the initial and final states of the system, but also it depends upon the path which is adopted for the process. Now we try to understand the work done in a cyclic process. Now first of all we define cyclic process. So cyclic process is a thermodynamic process in which the system returns to its initial state after undergoing a series of change, or we can retrace the system backwards. Or you can also say, like they have said here, when a system after passing through different states returns to its original or initial state, then it is called a cyclic process. So here we assume that this is the graph for a cyclic process, where it started from point A, goes to point B, and then again comes back to point A. So initial pressure volume state was at point A, and again finally it has reached back to point A. So we trace it and we see what is the work done. Now if the expansion takes place, so we show it from the point A, C, B. So the curve ACB is denoting the expansion of the gas, and work done by the gas in going from point A to point B, or from state A to state B, will be given as work done AB is equal to area ACB B prime A prime, ACB B prime A prime, meaning this portion. Now similarly, if the gas is compressed and from point B or state B it is brought back to state A, then in this case the work done is given as work done from point B to A is equal to area B D A prime B prime. So we notice that this portion, taking the upper portion, is bigger than the initial one where we had only this portion, the lower part. So if we have to find out the total work done or net work done, then that would be given as the total work done on the gas is WBA minus WAB. So if we subtract these two areas, then we will be left with the area enclosed by this curve ACBDA. So this is the work done in a cyclic process. Net work done on the system or by the system will be equal to the area enclosed within the curve. Also, if the PV curve is traced clockwise, then the net work is done by the system, and if it's done by the system, then we take it as positive. Or if the PV curve is traced anti-clockwise, then the net work is done on the system and we take the work done as negative. Now we will try to understand the concept of internal energy. So we know that any system consists of molecules, and these molecules have some kinetic and some potential energy. So we define internal energy as the energy possessed by the system due to its molecular motion or molecular configuration. Now the energy because of molecular motion will be its molecular kinetic energy or internal kinetic energy, and the energy possessed because of molecular configuration will be its internal potential energy. So total internal energy of a system is basically the sum of its kinetic and potential energy of the molecules which are contained in the system, and it is denoted as capital U. And this internal energy depends upon the final state of the system. It does not depend upon how it was achieved. It simply depends upon the final state. So the pressure, volume, temperature and internal energy, they are the thermodynamic state variable of the system or of the gas. Now as we are aware of the terms and we understand what do we mean by internal energy, the work done or the heat, let us define the first law of thermodynamics. The first law of thermodynamics tells us that if we supply heat to a system, how will that heat be utilized? So let's assume that Q amount of heat is given to a system. So this heat, if Q amount of the heat is given to a system, this heat will not be completely converted to the work done by the system or on the system. Some part of it will be used to increase its internal energy, and then the remaining part will be used for the work done. This is the first law of thermodynamics. Now if we assume that we have supplied a small amount of heat, then it will raise small amount of the internal energy and small amount of work will be done. So dQ is equal to du plus dW. From here we can also define the internal energy or change in internal energy du as the difference between dQ, that is the amount of heat supplied, minus the amount of work done. So this is the first law of thermodynamics, which states that if Q amount of heat is supplied to a system, then some part of it will be used to increase the internal energy of the system and the remaining will be used for the work done. And the change in internal energy, that is delta U, is given as the heat supplied minus the work done. Now this is the first law of thermodynamics. If small amount of heat energy is supplied, then there will be small increase in the internal energy, and that will be stated as du is equal to dq minus dw. Now this equation, depending upon different types of processes, can take different form. For example, if we assume that the process is isochoric. Isochoric means it is a thermodynamic process where the volume of the gas is constant or the volume is kept constant. So if the volume of the gas is constant, then change in volume, that is delta V, is equal to 0 because there will be no change. Volume is constant. So delta U is equal to Q minus W. W, we can see it this way, that we have du is equal to dq minus dw. But now dw is given as, dw is nothing but P multiplied by delta V. But since change in volume, that is delta V equal to 0, so this entire terms becomes 0, we have dW equal to 0. Substituting this in the first law of thermodynamics, we get du is equal to dW. Sorry, du is equal to dq, or we can also write it as dq is equal to du. That means whatever heat was supplied to the system will be used to increase the internal energy only when the volume is kept constant. That is for a isochoric process. Now again we have another type of process which is isothermal. In this process, the temperature of the gas remains constant. So we know that if there is no change in temperature, there will be no change in internal energy. Change in internal energy means change in temperature. So the first law takes the form, first law is delta U equal to Q minus W. So there is no change in internal energy. So this is 0 equal to Q minus W, or Q is equal to W. That means for an isothermal process, the entire heat will be converted to the work done. But please remember that this isothermal process, in an ideal gas, the heat absorbed by the gas is entirely used for work done by the gas, which is true only for the ideal gas cases, not in real systems. And then finally we have the adiabatic process, the processes where there is no heat exchange between the system and the surrounding. The heat can neither enter the system nor leave the system. So in that case, the first law of thermodynamics, delta U equal to Q minus W, takes the form, there is no change in, heat is allowed to enter or leave the system, so no change in heat. So delta U equal to 0 minus W, or delta U equal to minus W. So in adiabatic process, work is done on the system. If it is done on the system, that is, we have a negative sign here, and if the work is done by the system, then W will be positive. When the internal energy of the system increases, the temperature of the system will rise, and when the internal energy of the system decreases, the temperature of the system will decrease or it will fall. That's all in this AV. Thank you.